Okay, class. As promised, this will be our recorded lecture for the last section of Animal Science 102, which will be about feed processing. Now, why is it important for us to talk about feed processing? It is important because of three reasons. One, processing feed improves animal performance. If we will go back to the history of animal nutrition, in the earlier part of the century, what they do to feed pigs and chickens, as well as cattle, is to provide them different types of materials, different types of ingredients, provide them separately, and then they just allow the animals to consume those ingredients by choice. And it is the belief of farmers that the animals know what they need and they would consume the right amount of those ingredients to satisfy their requirements. And now we know that that is not true. It is important that all these ingredients are provided together in a mix and in the right proportions so that we can more accurately meet the requirements. And we can only do that by processing feed. Now, the second importance of processing is that it improves the mixing characteristics of the diet. Now, just imagine if you would feed them corn, and that corn is whole corn, and you mix them in the proportion that's needed in the diet. What do you think would happen? Well, two things will happen. One, that corn will not be uniformly mixed with the rest of the ingredients, which are often in ground form. And second, most definitely, that corn will not be fully digested by the animal. So, for it to be uniformly mixed into the diet, it has to be processed. It has to be ground in such a form and size that it can then be mixed together with the rest of the ground ingredients. And that will enable us to provide them the right proportion of nutrients that the animal would need. Then the last reason why processing is important is that it improves feed handling and feeder management. So handling in the farm, handling in the feed mill is improved by the ability of processing, and that is one of the purposes of pelleting, because pelleted diets are easier to handle. They do not get stuck into the feeders. They do not get stuck along the lines and augers of both the feed mill as well as the feeding systems in the farm. So that then allows, it allows us to make sure that the animal will be provided the feed when they need them. Now, what you see here in this figure is a schematic diagram of the entire feed manufacturing process. If you would go to a feed mill today, and it is a modern feed mill, you will go to this room called the control room. And in the control room, you will find the engineers that are managing the feed mill, and they're looking into this board. And that board would show this figure, and it kind of describes the entire process, and it tells the engineers what's going on, where the process is, through some of the lights that you would see on the board. Okay. Now, in this process, this is from bagging. This is from the intake of the delivered ingredients to grinding, mixing, pelleting, and bagging. But in the entire process, we'll talk about three areas or three processing methods that has the biggest impact on the quality of feed. That will be particle size reduction, mixing, and pelleting and conditioning. So we will focus on those three matters. So the first we'll talk about particle size reduction or grinding. So why is it important that we reduce particle size? I mentioned it a little bit on the importance of feed processing. So there are four reasons or four benefits of reducing particle size. So one, it increases or it improves feed digestion or digestibility of the feed. So as I mentioned, if you use whole corn, then most definitely the animal will not be able to digest the corn completely, because a big portion of the corn is within the hull of the corn. And then there is only a specific amount of time that the feed will pass through the digestive tract. So there's time limitation, there is limitation in terms of access to digestion, and that overall will reduce feed digestibility. And so reducing the particle size or grinding the material or the corn in this example will increase the surface area for digestion and would then lead to better digestibility of nutrients. And the animals can then get more energy, more amino acids, more nutrients in general from the material. The second is it improves the binding ability between particles. So I mentioned about pelleting a while ago. So pelleting is a process where the feed is heat treated, and with steam and with some pressure, it binds the material all together to form pellets. And the binding ability of these particles would be improved by particle size reduction, because the sizes of the particles would be similar to each other. The third benefit of particle size reduction is the improvement in mixing efficiency of ingredients. So as I also mentioned earlier, if we mix materials that are of similar sizes, then it's better in terms of mixability, and that also improves the uniformity of the mix, which means that if the animal would consume a kilogram of feed from the first bag and then a kilogram of feed in the last bag of the batch, they will be practically be the same, because the mix is uniform. And particle size reduction allows us to improve that mixing efficiency. And then finally, it increases particle homogeneity and prevents ingredient separation. If I am producing mash feed, then with particle size reduction or assuring the correct particle size, we could have a more homogeneous mix, and that will also prevent separation of ingredients across the sizes. Because if you remember, if the feed is is stored, and in time, what will happen is there will be separation of the particles. So if you have heavier particles, it would settle at the bottom of the bag, leaving the finer particles at the top. So that tells us that the mix is not uniform. So particle size reduction allows us to assure better homogeneity and prevents ingredient separation. Now, there are two types of equipments that are used in feed milling or for grinding raw materials. The first would be hammer mills. And the reason why they are called hammer mills is that they have swinging hammers. And those swinging hammers are attached to what we call a flywheel rotor. And as it rotates, those hammers swings, and as it gets in contact with the material that passes through the screen, it will smash that material, shattering it, and then the ground material that can pass through the perforated screen at the bottom of the hammer mill would be the correct particle size. So we can change the particle size by changing the screen in the hammer mill. Okay. And one of the good things about hammer mills is that it can process a wide variety of ingredients. Now here is a picture of a small hammer mill. This is not what you would see in large feed mills. This was actually taken from a smaller feed mill, a teaching feed mill. But the basic structure would be the same. So what you see on top what you see in this equipment is you have three basic parts. You find the screen, and the screen we could change based on the particle size that we desire for the feed type that we are producing. Then you have the flywheel rotor or the rotating hub, and then attached to that flywheel rotor will be the hammers. Okay. So in general, this is what happens. So you have the material that is placed into the inlet, and then that material comes in, passes through the discharge, and then along the line you will have a magnet, and I think it will be obvious why we need to have a magnet, and that is to prevent any metal to continue on into the grinding part of the equipment, and that would increase the life of the equipment. And then as the material comes in, that the flywheel rotor is rotating, and the hammers will hit the material that comes into the breaker plate, and then obviously it will be shattered into smaller pieces, and the particles that would flow out of the screen, it will go out of the screen into the material outlet, and that allows us to ensure that the particles are of the correct particle size. So a very basic principle. Now, the other type of grinding equipment is called the roller mill. And again, just like the hammer mill, the reason why it's called a roller mill is that it grinds the material by rolling. Okay, it's used for rolling, cracking, flaking, and steam flaking grains. And those materials are actually used for ruminant diets. So what happens is the grain passes between two rotating cylinders, and those rotating cylinders we can adjust the distance or what we call the roller gap, and the speed of rotation, and that is how the engineers can control the particle size that would come out of the roller mill. Okay, so the speed of the rolls determines the size and the shape of the particle. So the picture you see here is an example of the roller mill, and as you see in the middle, you see three sets of rolls, and it has handles where the engineers can control the distance as well as the speed of the rolls. So here you see the grains in the material inlet goes into the roller mill, and those roller mills rotate in opposite directions. Okay, one is clockwise, one is counterclockwise, and as you could imagine, as it goes through, as the material goes through the rolls, it is compressed, sheared, and ground, and then at the end, it is at the particle size that we desire. Now, one of the advantages of the roller mill is that it can grind very small particles. Like, for example, sorghum. Sorghum has a very small particle size. It's like mung bean in terms of size, and actually even smaller. And usually when we grind sorghum in hammer mills, it's very difficult to grind. So at the end, you end up with whole grain of sorghum when you use the hammer mill. But in roller mills, even the small grains can be ground easily through this equipment. So that's the advantage of the roller mill versus the hammer mill. It has more flexibility in the type of ingredients that can be ground. So what again are the benefits of particle size reduction? So here is a classic study done at Kansas State University. So what you have on the x-axis is particle size, and the unit of particle size is microns. And the lower the microns, the more fine or the finer the grind is, or the particle size is. Okay, so what you see here is particle size on the x-axis, and then the digestibility of crude protein, energy, and dry matter on the y-axis. And as you could see, As particle size reduction decreases, or the finer the grind, the better is the digestibility of nutrients, protein, energy, and dry matter. So again, the reason for that is it increases the surface area for digestive enzymes to access, and that enables them to fully digest the nutrients that are in the material, and that results to better digestibility. So here you see a picture of ground corn at different particle size. So on the top is 1,200 microns, 900 microns, and then at the bottom you have 700 microns, and then 500 microns. So you see, as we go down from 1,200 to 1,500, from 1,200 to 500, you see a finer grind. Okay, and some work again from Kansas State showed that for every 100 micron reduction, there is an improvement in feed efficiency by 1.2%. The next question then is, how do we check for particle size? And there is a method called particle size test. This is using different sets, a set of sieves with different perforated screens or sizes of perforated screens, and inside the sieves you would have agitators or dispersing agents. Okay, and this particular method that you see is called the Rotap method, and the reason why you called it a Rotap method is the set of sieves are placed into this Rotap shaker, just as you see in the figure, and then this shaker would rotate the pans in 10 minutes, and on top of the pan is a part of the equipment that taps downwards. Okay, so that enables the material to be tapped and flow through the set of sieves. Okay, and after 10 minutes they stop the machine, and then they take the pans, and then they weigh the feed or the material that is left in each pan. Okay, so this is what I was describing. So you get a sample first of the ground material. You put 100 grams of the material on the top sieve. Okay, you close the machine, you put it in the Rotap for 10 minutes. As I mentioned, it rotates, and then at the same time it is being tapped on top, and then at the end of 10 minutes we take the material that's left in each sieve, and then we weigh. Okay, and then after weighing, we have a spreadsheet where we have the sieves from the largest to the pan. Okay, so you see US sieve 4 having a micron size of 4,760, and then as we go down you see micron size decreasing, and then at the pan, which is the bottom, you have a micron size of 37. So the weight of the material that we did the test, we enter it in this spreadsheet. Okay, and then at the end it will tell us what would be the particle size. So in this example, the particle size is 924 microns. Okay, and in this method you could also see the range. The range is from 431 to as large as 1,983. So quite a big range. So it's not just the average particle size, but also the range of the particles. So once we've measured the particle size, we then look at the standards. So for every raw material that's ground, particularly the cereal grains, there is a recommended particle size, and this is a product of previous research that's been done to see what will be the correct particle size to optimize digestibility and performance. So on the top you see corn, And then for sows, the recommended particle size is between 600 to 800 microns. That's the same for growing pigs and broilers. But in layers, they need a larger particle size. Okay, and that is to enable the older bird to have a better, a more muscular gizzard, and that allows them to get more nutrients from the feed. Okay. Now for sorghum, it's still not known what would be the appropriate particle size in sows, but in growing pigs and broilers, it's about 600 to 800 microns, so just like in corn. And then for layers, it's about 800 microns. And then for wheat, again, there's not a lot of data on wheat. For sows, layers, and broilers, although there is some work in broilers that recommends wheat being fed to be fed to broilers or even layers as whole wheat. Okay, and that is again related to gizzard, the gizzard size. And again, for growing pigs, it's between 600 to 800 microns. So the feed mill would have this type of recommendations, and that will be the standard. And so if the particle size, actual particle size, does not meet these standards, then they have to readjust. Maybe there's a problem with the mixer, the grinder, maybe the screen, maybe the hammers, and so they'll go back, check, and if everything is correct, then probably they'll just change the grinding time, and so they could meet the standards. Okay, so what are the benefits of a consistent particle size? Okay, so one, there's less feeder bridging and plugging. So later I'll show you some pictures what that means. In commercial farms that uses automatic feeders, that would mean fewer feed lines that are plugged, because remember, if the feed lines are plugged, that means feed will not flow through the lines, and so the feeders at the end of the line would be empty, and that can lead to out of feed events. There will be fewer ulcer outbreaks in pigs. Gastric ulcers is a problem, particularly for fine ground meal. So if the feed is too fine, it can lead to greater incidences of gastric ulcers. And when there is a gastric ulcer, there is blood in the stomach, and the animal actually will die because of hemorrhage. And so when you open these pigs that have ulcers, you'll see their stomachs full of blood. And usually it's the larger pigs or the faster growing pigs in the group that will be affected. So that will be an opportunity lost from the operation. That's why we need to ensure that we use the correct particle size and a consistent grain particle size. And then finally, because of the improvement in energy digestibility, that will facilitate higher energy density of the diet. Okay, so this is a picture of a bin. So this is a bin that's outside of the building, and it is used to store feed. And as you see, the bottom of the bins are transparent so that the farmer can easily see if there is bridging. And in this case, you see that there is bridging, which means that the feed is not flowing properly at the bottom of the bin, and so as the motor runs, there is no feed that actually flows out of the bin. Then this is a picture of feed bridging. This is already at the feeder. So if the particle size is inconsistent, you see this feed bridging, and when there is feed bridging, there is ingredient separation. So as you could see, in the middle there is the bridge, and so usually what is left here in the middle would be the fine materials, the finer ingredients, and so that means the mix that comes out of the pen of the feeder is not uniform, and that can have negative impacts on performance. And then the worst part is if there is feed bridging, or there is plugging along the lines, then out of feed events can happen. So by the term out of feed, it means that the feeders are empty, and when the farmer finds out that it is empty, they will fix the problem, and so suddenly feed will flow out of the feeders. But because pigs did not eat for quite some time, they will rush into the feeder and they will fight over the feed, and that could create stress, and stress would then lead to negative effects on performance. So welfare issues and even performance effects have been shown when there is a high incidence of out-of-feed events. Now, the benefit of grinding is improvement in digestibility, but there are also disadvantages if we grind the feed too fine. And when we say too fine, that means it is less than 600 microns. So for one, it increases dustiness, so the feed is more dusty, and dusty feed can lead to some respiratory issues. It can increase electrical costs because one, you're grinding longer, and grinding is an energy expensive process, and that is too expensive for the feed mill. And then second or third, it increases the time of grinding, so that also leads to increase in electrical cost. And then also, if there is increased time in grinding the material, then that would mean it will reduce throughput of the feed mill. So when we say throughput, that is the amount of feed that the feed mill can produce per hour. And in a feed mill, that is also a negative issue. It's a problem. So that can also have an effect on productivity of the feed mill. And then in the farm, it can decrease feed flowability. So feed plugging or feeder lines are plugged. And then, as I already discussed, it increases the incidence of gastric ulcers. So that's why it's important that we keep our particle size at the recommended standard. So that will be between 600 to 800 microns. So that optimizes the benefits in terms of digestibility, but at the same time optimizes throughput and electrical costs. So that what I mentioned is demonstrated by this study by Wondra in the late 1990s. So you see at the bottom on the x-axis is the particle size of the feed, so from 1000 to 400 microns. And then you have energy consumption in kilowatt hour per ton on the y-axis, as well as production rate, and that's tons of feed per hour of production. So as you could see, as particle size decreases from 1000 to 600 microns, you see the energy consumption. And then when you grind from 600 to 400 microns, you see a big increase, or actually a doubling of the energy consumption from 4 kilowatt hour per ton to 8 kilowatt hour per ton. At the same time, you see production rate at around close to 3 tons per hour. And then when you grind finer from 600 to 400 microns, you see a significant decrease in production rate from close to 3 tons per hour to a little over 1 ton per hour. So that is a negative, those are the issues when we grind feed too fine. Okay, so the next processing topic would be mixing. So what is our goal when we mix feed? So here is a figure that kind of describes the type of mixes. You have a perfect mix on the left, so it's like a what you call that, chessboard. And then you have a random mix, there's no order. And then you have a segregated mix. So here you have more white squares on the top than on the bottom. Okay, so what is our goal? Our goal is to have a perfect mix. Okay, so we want to get it as close to a perfect mix as possible. So there are two types of mixing equipment that is used in the feed industry. So the most common one is called the horizontal mixer. And in this figure, you see an example of a horizontal mixer. And inside that horizontal mixer is a rotor. And then around the rotor would be ribbons. So this is an example of a ribbon type mixer. Okay, so this rotor would obviously rotate, and that would then mix the feed horizontally inside that mixer. So what is the advantage of a horizontal mixer? So our goal is a uniform mix, and the measure of uniformity is the coefficient of variation, or CV. And as you could see in this figure, you have the mixing time on the x-axis and then the percent CV on the y-axis. And this is for a double ribbon horizontal mixer. So our goal is to get the CV of the mix to around 10%. So when we say it's 10% and below, that's a uniform mix. And for our double ribbon horizontal mixer, it takes about 2.5 minutes to get to 10% CV. So that's pretty good. And then we add a half a minute to 3 minutes, and that will give us a CV of around 5%. Okay, and beyond 3 minutes, you see that there is no more further improvement in CV. So this means that there is no such thing as over mixing, that if you mix beyond the correct time of mix, it will go back to a higher CV. So that's not true. It will just stay that way. But that makes it longer, the time is longer, and then you spend more electricity. That's why we mix at the appropriate mixing time. The second type of mixer is the vertical mixer. So unlike the horizontal mixer, it mixes the feed vertically. So that's why it's called a vertical mixer. And so you have a picture here on the left, an example of a vertical mixer. And this is what you would more often see in smaller feed mills or in farms that mixes their own feed. And the reason is because the vertical mixer is a cheaper equipment than the horizontal mixer. And then the second advantage of the vertical mixer is that it takes less space compared to a horizontal mixer. Okay, so inside the vertical mixers, you would have two augers, and those two augers would have blades, and it will rotate in opposite directions. And as you could see from the figure, there are two main mixing zones. The one is at the bottom, okay, and then the other one is on the top of the two augers. So those will be the two main mixing zones in a vertical mixer. So if we go back and look at the mixing time that's required to 10% CV, you could see that it takes a lot longer time. So to get to 10% CV using a vertical mixer, it will be about 10 to 11 minutes. And then probably to get to 5% CV, it will be about 15 minutes. So it takes a lot longer time to get to a uniform mix. So if you will be working in a feed mill or in a farm, or you'll be formulating in a farm, one of the things that you really need to check is what is the type of mixer that they use, so that you could recommend appropriately the correct mixing time when you make your feed. Now, there are some mixer problems that we need to take into consideration. So one of the issues is liquids, and liquids are added into the mixer through spray nozzles. And here you have a spray nozzle. So if that spray nozzle is covered by feed, then when the liquid, and usually the liquid that's sprayed is oil, which is, remember, it's an energy source, or maybe methionine, which is also added into the feed. There are some sources that are added into the feed as a liquid. So if it is covered, then when it sprays, it might not spray, and that can then affect the diet and the quality of the diet. So we have to ensure periodically that the liquid spray nozzles are not covered with material. And then the other problem is material buildup in the blades. So if we have a lot of material buildup in the blades or feed that gets stuck in the blade, then that can also have some effect on the uniformity of the mix. Some other problems are materials on the ribbons. So just like what I've shown you. So that means if there's a lot of material that gets stuck on the ribbons, and that happens when we mix the liquids improperly, like the oils. Okay, so that would then mean that when we bag the feed, if we're expecting 1,000 tons of feed, then most likely we will not get 1,000 tons or a one ton. So that means a big portion or a significant portion of the feed is left on the ribbons. So this has to be cleaned periodically in such a way that we could prevent material buildup on the ribbons. And so just like the picture on the right, the reason why material is left on the paddles is because the liquids are on the paddles as well as in the axle. And so when material is in the mixer, it will get stuck on the paddles, and that prevents it to be mixed into the rest of the feed. And another problem would be the formation of fat lumps. Okay, so when you look at a mix of feed, you see balls of fat. And obviously that means the fat is not properly mixed into the feed, and that again would affect the uniformity of the mix. Okay, so how do we then test for the uniformity of the mix? So we do that by doing what we call a mixer performance test, and that is part of feed quality assurance. So periodically, it depends on the feed mill. Some feed mills do it more regularly. Some do it 6 months. Some do it once a year. But obviously, the more regular you do it, the better. So what they do is they check mixer performance by getting samples of feed, usually 10 samples of feed, either from different areas of the mixer or as feed comes out of the mixer. And they get 10 samples from different bags that comes out of the mixer, and then those samples are then analyzed for salt or a marker. And the way they will do it is they will calculate for mixer CV. They will analyze for, let's say, salt, all the 10 samples, and then they will calculate the standard deviation and then divide it by the average percent salt times 100, and they get the percent CV. So why salt? The reason why salt is usually selected is because one, salt is one of the micro ingredients. The inclusion in the feed is not very high, and at the same time not very low. So if the CV of the salt is good, then we assume that the CV of all the ingredients is also very good. Okay. So once we know the CV, we then compare it to a standard. So by the way, this is an example. Here, instead of salt, they use a marker called a Quantab. And they analyze the Quantab for the 10 samples. And the reason why they use these markers is because when we think about it, the added salt in the feed is not the only source of salt. If you have ingredients like animal protein sources or fish meal, they can contain salt as well, and that can then add to the variation. As an alternative, they use other markers like Quantab. Okay, so here, in this example, you see they measure the standard deviation, which is 0.02. the mean quantum reading is 0.19, and then the CV is 9.65. So what is the standard? As I already indicated earlier, it's 10%. So 10% and below, that's excellent mixer uniformity. That means there is no corrective action that needs to be done. But if the CV is 10 to 15%, it is good. But that also means that we need to increase mixing time by around 25 to 30%, so that hopefully that can bring down the CV to 10% and below. If the CV is 15 to 20%, then the rating is fair. And the corrective action would be to increase mixing time by 50%. Okay, so if I'm mixing 2 minutes, then I'll mix 4 minutes. And then I'll start looking at the equipment. Maybe look at worn equipment, maybe the blades, maybe the paddles. Maybe we are overfilling the feed, the mixer. Overfilling means putting feed above the capacity. So if it's a ton of feed, then it's putting more than a ton of feed. And another problem would be underfilling. So that means using a large mixer for a small batch of feed. So the standard is it should be between 50 to 80% of the capacity of the mixer. Okay. And then the other issue is the sequence of ingredient addition. So there is a correct sequence of mixing. So the first should be the dry mixing, and then you have what we call wet mixing. The first is the dry mix. So we start with the macro ingredients, so corn, soybean meal, the large ingredients, rice bran, wheat pollard. And then it will be followed by the premixes, the smaller ingredients, the micro ingredients. And then after mixing the macro with the micro, the last to be added should be the liquids. So if you could just imagine, if we put the liquids first, then potentially when we mix the smaller ingredients, it could get stuck into the liquids, and that would prevent its mixing into the feed. So proper sequence should be followed. And then finally, if the CV of the mixer is more than 20%, that means it's a poor rating. That already tells you there is really something terribly wrong. You need to probably consult the manufacturer of the equipment and maybe look at replacing the mixer already. Okay, the third aspect of processing that we'll discuss would be conditioning and pelleting. So what is conditioning? So the objective of conditioning is to improve the pelleting of the material, and we do that by including or injecting steam into the material so that moisture would be absorbed, and that would then gelatinize some of the starches in the material, and that would improve the binding ability of those pellets. So the purpose of feed mash conditioning is, one, it raises the mash moisture and temperature cook. So in a way, it's a cooking process. It activates the natural adhesives that are found in the ingredients. It also softens the feed particles so that it will improve surface binding when it is compressed in the pellet machine. Conditioning also increases pellet die lubrication so that the feed would easily pass through the die or the holes of the die. And then finally, because there's heat that is injected into the feed, that can also destroy some microorganisms or deactivate some anti-nutritional factors that are heat sensitive. So there are different types of conditioners, and the difference is mainly on the number of conditioners on top of the pellet mill. And obviously, the more conditioners, the greater is the amount of conditioning time. So on the left, you have a single pass conditioner where you only have one barrel of the conditioner. Then you have a double pass, which has 2 barrels of the conditioner. And then you have a triple pass, which has 3 barrels of the conditioner. So obviously, the triple pass would have a greater amount of time for conditioning than both a double and a single pass. So what happens is, so you have mash, and it enters the conditioner, and in the conditioner there's steam that's injected into the material that then conditions the feed, and then it is mixed inside the conditioner so that the feed would be properly conditioned. And then at the end, you have conditioned mash that will enter the pellet machine. So it's higher in moisture and higher in temperature. So that will make it a lot easier for the feed to pass through the pellet die, and that would improve binding ability, and you would have better pellets, more durable pellets. So here you have a picture of pelleted feed. So pelleted feed would vary in terms of size and shape and length. Okay, so it's really dependent on the feed type. So for example, for younger pigs, would give us smaller pellets, and then older pigs, we will give them bigger pellets. And then if you put the pellet, a pellet that just come out of the machine, the pellet machine, and look at it under the microscope, so it looks like a cooked food, cooked material. So that tells us that the pelleted feed is partially cooked. So what's the benefit of pelleting? So one, it improves palatability. That's why feed intake is usually higher in animals given pelleted feed, particularly in pigs, compared to those fed mash feed. There's less feed wastage, unlike mash feed. That's the biggest difference between the two. Because of the heating process, it destroys the pathogens or microorganisms. There is less ingredient segregation because, again, they are bound together. The ingredients are bound together, unlike in mash feed where they can easily segregate in time. And then it has better flowability. There's no issues with plug feeders or bridging or out of feed events. And then for a nutritionist, pelleting provides formulation flexibility because they can use more alternative ingredients. They can increase fat levels that they cannot do in mash feed. So here again is a picture of a pellet mill. So on top you see the yellow conditioner. It's a single pass conditioner, and then at the bottom the one with a sign of CPM. That's a brand of a pellet machine, so that's the pellet mill. And then what's connected to the pellet mill is the pellet die. So you see the one with feed sticking out. So that's the pellet that comes out that's pressed into the pellet die. And then there's a cutter, so you could set the length of the pellet so it will cut the pellets into the size that you want. So here is a picture of different pellet mill dies. So you see there are pellet dies with smaller holes compared to some. So usually the bigger pellet dies, that's for ruminant diets. Smaller will be for swine or even broiler diets. Okay, so again, what are the advantages of pellets versus mash, and the other way around, mash versus pellets? So the advantage of pellets is you could reduce particle size, even smaller, less than 600 microns. You can do that, and that would actually improve pellet durability. There's higher inclusion of alternative ingredients, so you have a better choice. You could also increase the inclusion of alternative ingredients. And the reason why that is important is because in mash feed, what farmers would do, especially in commercial feed, is they can easily look at what are the ingredients, and so they could tell if it's corn or if it's wheat or if it's something else. And if they see something else that they're not familiar with, then they don't use the feed or they don't buy the feed, and that's a problem, because the reason why we use alternative ingredients is to reduce the cost of the feed. And so in pelleted diets we can do that much more than when we manufacture mash feed. The other thing that we can do with pelleted feed is we can further include fat in the diets, unlike in mash, because if you have high inclusions of fat, it becomes wet. But in a pelleted feed, it is much easier to increase the level of fat. And then there is no issues with flowability. There's less dust, and then there's an improvement in feed efficiency compared to mash. In mash, again, the grain particle size have to be greater than 700 microns, and then it's usually a grain-based formula. You cannot use many alternative ingredients, but the biggest benefit of mash is it has lower manufacturing cost than pellet. Okay, so if you are making pellet, if there's an extra step, that means it's usually a more expensive feed than mash feed. But if you're making pellet feed, it's also important to look at pellet quality. So like in this picture, this is a feeder inside the farm. You see pellets inside the feeder, but in the pan, it is already fine mash. That means that the pellet quality is not very good. It easily disintegrates into fine, and that's not good. So pellet quality is an important issue, and you see here there are a number of factors that affect pellet quality, from feed formulation to cooling, conditioning, the dye that is used, the particle size, and the throughput of the feed mill. And what you see here is the contribution, and then who contributes to it, the nutritionist or the feed mill. And as you could see, the nutritionist at most has about 25 to 45% contribution, and then the feed mill contributes about 50 to 75%. So which means that a bigger a bigger contributor in pellet quality would be how we process the feed. So this is a good study that demonstrates the importance of pellet quality. So here they fed pigs mash and pellets, and then they have pellets with 20, 40, and 60% fines. So fines are the ground pellets. Okay. So what we see, if we have good pellets, okay, then we see the improvement in feed efficiency. That's a fairly good improvement in feed conversion ratio. Okay. But if our pellets are of poor quality, as less as 20% fines, we see that the feed efficiency is just the same as the meal-fed diets. So we lose the benefit of pelleting. So it demonstrates the importance of making sure that we produce good quality pellets. So how do we test for pellet quality? So what we do is a pellet durability test. So this is called the tumbler or tumbling test or PDI test. So you put a certain amount of feed into the tumbler, and then you tumble it for 10 minutes, and then you give some increase the agitation by putting some hex nuts, about 3 to 5 hex nuts inside the tumbler, and then it will tumble within. And then after tumbling, you get the feed, you separate the whole pellets, and then you divide the pellets and then over the initial weight of the feed. Okay, so this is the PDI procedure that I described. So you get the sample, you remove the fines, you weigh about a half kilogram, you put it in the tumbler for 10 minutes. After tumbling, you separate the whole pellets by screen, and then you weigh, and the PDI will be calculated as the weight of the pellet after tumbling over the weight of pellets before tumbling. So the standard is to get it as high as probably 95% and above. Okay. So different feed mills would have different standards, and then it will also depend on the feed type, but usually 95% will be good enough as pellet durability. Okay, so we have two additional steps that we'll talk about, and these are some of the recent developments in feed processing. So these are the processes called expanding and extruding. So first, the expanders. So expanders are something like conditioners, except that there is greater pressure that is applied into the feed. So there's high pressure and more conditioning, and then that allows us to improve the gelatinization of the feed. And if pelleting temperatures would be somewhere between 70 to probably around 80 degrees Celsius, expanders temperatures would be a little bit over 100 degrees Celsius. And so that is the reason why it is a good method for feed sterilization. So for countries that have very strict rules on feed safety, uh, they would apply or put an expander on top of the pelleting machine, so that will then sterilize the feed, and that will ensure better protection against potential pathogens. So here you see where the expanders are placed. So you have the conditioner, as we have discussed, and then below the conditioner is the expander. So the conditioned mash will enter the expander, and then there's a lot of pressure that is applied, and that is through the plunger gap, the one you see at the end, like the arrow shape. Okay, so feed has to pass through that plunger gap. That's the pressure that is applied, and then before it enters the pellet machine. So there's higher temperature, higher pressure, which will then improve feed sterilization and gelatinization of the feed. So here is a picture of an expander. So the one you see on top is the silver one is the conditioner, and then the red tube is the expander. And then again, in this example, they have another conditioner at the bottom before it enters the pelleting machine. Okay, so there are some suggestions when we expand feed. So the first is piglet feed is not expanded, and the reason is because many of the specialty ingredients are negatively affected when they expand them, like specialty protein sources. So protein digestibility decreases, and then the other is the stability of some vitamins are also affected because they are subjected to very high temperatures. Okay, so piglet diets we don't expand, and today expanders are more often used in poultry diets than in swine. And again, that is because of feed safety issues. Salmonella is a major issue in poultry, so not much in swine. And so the use of expanders play a very important role in ensuring sterilization of the feed against salmonella. Then the third is it is relatively expensive. So the only justification for the use of expanders is the example I gave you, the feed safety regulations. Okay, and then if pellet throughput is an issue, then maybe expanders can help improve both quality and throughput. So those are probably the only reasons why we would put an expander in the mill. Then the last would be extrusion processing. So again, it is a heat treatment that is applied to the feed, and compared to both the pelleting process and the expansion process, the extrusion process is has higher temperatures. It's about 135 degrees Celsius, and then there is a lot more pressure that's added into the feed, and that's why they expand and they form different shapes. So there's air that's pressed into the material. So that would shear, gelatinize, and change the structure of nutrients. And as they exit the extruder, they expands because there is less pressure on the outside environment than inside the extruder. That's why you can create material like cheese puffs, breakfast cereals, pet food. Those are all extruded feed. So if you notice, they are lighter and they're fluffy. Okay, and that is because of this phenomenon. Okay, so here you have a picture of a small scale extruder. It's not a very good picture. But the extruder is at the bottom, okay? And as the feed passes through the extruder, there's higher temperatures that's applied, 135 degrees Celsius, and there very extreme pressure that is applied as it goes out of the extruder. And it has a die, and through the die you can change the shape of the output. Okay, so if you want heart shape, if you want letter shape, if you want flower shape products, you can do that by changing the die. So here is a picture of different types of feed that's extruded. So you see majority of the ones you see on top are pet food. So if you have pets and you buy pet food, I'm sure you've seen extruded feed. And then at the bottom, there's our fish feed. Those are also extruded feed because some species would require floaters or floating feed so that the farmers can easily see if the fish are eating. And some of these species are surface eaters. Then some they extrude feed so that the feed will be slow sinkers. Okay, so they don't just simply sink into the bottom. So those are the reasons why extruders are used in the feed industry, and most often it's for the pet food industry as well as for the aquaculture industry. So again, the benefit of extrusion is compared to pelleting is it increases starch gelatinization. This is true for both wheat diets and oat diets in this study. And then also here, this is digestibility in broilers or starch digestibility in broilers. With extrusion, they saw a significant increase in starch digestibility for the wheat diets. Okay, so that's the end of our discussion on feed processing. So hopefully by now you know why feed is processed. Hopefully you've also learned the different types of processing equipment for grinding, for mixing, and then for the heat treatment processes like conditioning, pelleting, expanding, and extruding. Hopefully you understand the importance of particle size reduction, and then by now you can hopefully differentiate between what pelleting is, extrusion, and expansion. So with that, thank you very much, and I wish you all the best in your exam on Wednesday. Thank you.